this last unit we have is actually a part of the pre-cal curriculum. They do this way back in the fall. This is something they did in September. But that's what you're ending up with here. So I've already got some videos recorded for these lessons that I did, and it's exact same lessons that the pre-cal did to start the year. So I'm going to be reusing some of those videos. So I'm going to splice this in. And so if you hear this video talking about pre-cal stuff or anything pertaining to that class, you can ignore that. You know, you're the Algebra 3 class, and this will be pertaining to you for these lessons. So here we go.
Starts out lesson 1, defining a polynomial function. That just means a polynomial means it has many terms, right? It'll have x to the third, maybe an x and a constant, or an x to the fifth, and x to the fourth, x to the squared, and a constant, you know. So it starts talking early about, in lesson 1, just the quadratic functions, because quadratics are so commonly used that we have a whole lesson just about quadratics. I'm going to put up my camera there. So, of course, the standard form of a quadratic function, as we see that, would be ax squared plus bx plus c, right? Where you have x squared is the largest term, which makes it a quadratic function. And when we graph it, it's going to look like a parabola, right? It'll look like a parabola when you graph it. If it's positive, if the a is positive, it's going to be up. If the a is negative, it'll be upside down. Okay, quadratics are nothing new to you guys. We've dealt with that. This one talks a lot about, though, this is the standard form that we see quadratics. We talk about the vertex form here. So the vertex form is a of x minus h squared plus k. And when you have it in the vertex form, then it tells us some things about it. It tells us that the point hk is the vertex. And that the axis, the center of that parabola, right, the axis of symmetry for that is going to be the line x equals the h, whatever that h is. So when we have it in vertex form, we do it like this. And it talks about converting it. Let's say if we have a quadratic, and let's say this is our quadratic, 5x squared plus 10x plus 6. All right. We don't know a whole lot about how to graph that right off. We'd put it into our graphing calculator or put it on our graphing website and let it graph it. But we can convert that to vertex form and learn a lot about it. So let's factor, first off, this right here. So let's say it equals 5 times x squared plus 2x plus 6. And in order to convert this, go back to completing the square, which you've done a little bit in the past. So we're going to bring that back as a reminder. We need to make this a factorable quadratic right here in the middle. So to do that, we've got to figure out what do we need to add. And what we do is we take that middle, that term right there is going to be the middle term. We divide it by 2, and then we square it. Divide it by 2 and then square it. So if we take that and divide it by 2, that means it's 1, and 1 squared is 1. So we need to take and add a 1 on the end. But we also need to subtract a 1, or else we've changed the equation. Right? So we add 1 and subtract 1, so it's still the same equation on there. So now this part we can factor. This part we'll need to pull out. But remember, it's in parentheses being multiplied by 5. So when we pull out, it's going to be a negative 5. So we have 5 times x squared plus 2x plus 1 minus 5 plus 6. Because we do have a number outside here that's affecting that minus 1 that we added. So now let's factor it. This factors to x plus 1, x plus 1. Let's see, minus 5 plus 6. So we can simplify that to 5 times x plus 1 squared plus 1. This is now vertex form. So we know the vertex of this quadratic equation, which started right here. The vertex is going to be at -1 because this is x minus the h. Since we have x plus 1, the h must be a -1. So the vertex is at -1 and the k is 1. That's where the vertex is. And since this is a positive out front, we know it goes up. So if we're graphing that, we can go over to -1 run right there. And that's going to be the vertex, and it's going to be going up. And we know that is the line of symmetry. Right, x equals -1 is the line of symmetry. So we know what the graph is going to look like basically. Now the 5 is going to make it where it's not just a standard, it's going to be a vertical stretch on that. But we know a little bit about it where we can just do a hand sketch of it, not necessarily a graph. We can do a hand sketch without having to do any points because we know where the vertex is and we know that it goes up. So there is a lot of good stuff from being able to convert that to vertex form because it gives us some more information about the quadratic. So factoring it, being able to factor that. Sometimes, they don't factor well. We're going to use the quadratic formula. Everyone remember the quadratic formula. Let's do a refresher on that. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And that one goes back to the standard form, ax squared plus bx plus c. You can always use the quadratic formula. I'll post a video in Google Classroom in the quadratic formula, just a funny story from college. It's about 4 minutes. I'll post that later if you want to watch it. It's kind of a funny story. It's where some of my video intro comes from. Some of the scenes from that made it to my video intro. That is the quadratic formula. So just keep that in mind. So I want to jump to the second lesson now. The first lesson is just all about this: vertex form, quadratic formula, factoring, quadratics. That is not anything new. But the second lesson has some good stuff that we want to talk about. So we're talking about the general features of polynomial graphs, right? So when we have just anything that's a polynomial, which means it has multiple terms, x to the fourth plus x plus 1, right? Just a polynomial, poly being many terms. General features. And it'll talk about this in the lesson. For one thing is they are continuous. Continuous. That's a U. That means when we graph them, they're going to have no gaps, right? If we're graphing it, there's no point where we don't have gaps in it where we lift our pencil. We can graph it continuous like that. And then the other thing is it's smooth. It doesn't have a point like that. There's no points in the graph. It's going to be a smooth, continuous graph. So smooth curves, right? So that's what we're looking at. Smooth, rounded curves, no sharp points. That's some of the features when we graph a polynomial that we understand about that. But we talk about in this two things: the binomial theorem and Pascal's triangle. Pascal's triangle. And this basically helps us be able to take shortcuts. If we have a plus b to a power, right, some power, if we have it is 0, we know it's going to equal 1, because remember, anything to the power of 0 equals 1. If we have a plus b to the first power, that just equals a plus b, right? If we have a plus b to the second power, we'll end up, that's a plus b times a plus b, which is a squared plus 2ab plus b squared. And it gets longer and longer. You can only memorize so many of these. A to the third power plus 3ab or 3a squared b plus 3ab squared plus b to the third power. There develops a pattern in all of this. there's a pattern. And if we talk about Pascal's triangle is the triangle of that pattern. And it looks like this: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And we can continue this because each row is made up by, you put a 1 up front, you put a 1 at the end, and then the middle ones are adding those two together. 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. And we can continue and add more rows and add more rows. But what this tells us is this is the pattern. When we have a plus b to the 0 power, it's going to equal 1. When we have a plus b, it's just going to be a to the first power plus b to the first power. Here it's going to be a to the first power, or a squared, I mean, because we square, you do whatever the squared is here, plus 2, there's a 2 in front of the ab, and then b squared. And then you get, where are we at? The third power. A to the third power. And notice it goes down. A to the third power, A to the second power, A to the first power. And then A to the 0 power, which is just 1. Where the B does just the opposite. B to the 0 power, B to the first, B to the second, B to the third. See that pattern? You got A to the third, A to the second, A, and then it's just 1 here. And B does just the opposite. Nothing there. B, B squared, B to the third. And then the coefficients are right here. 1, 3, 3, 1. That's the coefficients. 1, 3, 3, 1. If we did A to the fourth, the coefficients would be 1, 4, 6, 4, 1. So what Pascal's triangle tells us is we could already jump ahead and know what the coefficients are. So if we had A plus B to the fourth, because we already have that here on our triangle, we know that A's would be A to the fourth, A to the third, A to the second, A, and then just 1. This would be 1 for that. We'd have a B, we'd have a B squared, we have a B to the third, and we have a B to the fourth. And then the coefficients would be just 1 plus 4 plus 6 plus 4, and then a 1. Just plus. So that would be the pattern of the A plus B to the fourth right there. 4, 3, 2, 1, 0, 0, 1, 2, 3, 4 for the B's and these coefficients. So let's look at that with an actual number, or an actual, let's put something there, x minus 3. And let's make it to the fourth power, x minus 3 to the fourth. It does give this example in your textbook as well. So with x minus 3, that's our A and our B, right? So we know the pattern is this pattern here. So we would start out with x to the fourth. That would be our first term. Then we'd have plus 4 times x to the third times negative 3 to the first power. Plus, now we know it's 6 times x squared, b squared, negative 3 squared, times 9. Right? Or negative 3 squared. Then plus 4 times x, and then b to the third power. Negative 3 to the third power, which is negative 27. And then at the end would just be negative 3 to the fourth power, which is 81. We can simplify this. So it'd be x to the fourth, 4 times a negative 3, negative 12x to the third, 6 times 9 plus 54x squared, 27 times 4 minus 1, it's a negative 27, plus 81. So Pascal's triangle is a shortcut for us to do x minus 3 to the fourth power. Instead of writing x minus 3 4 times and doing all the distributing and multiplying everything times each other, and eventually, after several lines of math, we would get to this. We can just jump straight to this, knowing Pascal's triangle. It's pretty cool. It's a pretty cool thing. You say, well, that's great, but what if I want to jump down to the 10th line? I got to do a lot of triangle to get there. That's where the binomial theorem helps us out. The binomial theorem looks like this. NCR. Okay, and I'll explain this in a second. It goes in apostrophe, exclamation, R exclamation, N minus R exclamation, right? And let's have a reminder of what exclamation is. If I have 5 with an exclamation point after it, that's equal to 1 times 2 times 3 times 4 times 5. That means you multiply every number from 1 and to that number times each other. So 1 times 2 is 2, times 3 is 6, times 4 is 24, times 5 is 120. So 5 apostrophe equals 120. This, let's use this and talk about, okay, what does that mean? How does that help me? So this will help you find those coefficients without having to do everything up to it. So let's say we have that x minus 3 to the 4th again. So the n, this n right here is whatever power it is. So that would be 4th coefficients. And what we got to do is we got to check each one. This would be for r equals 0, 1, 2, 3, and 4, because we need to know all 4 of those. So if we want to know what the first coefficient is, we'd put a 0 in for the r. So this would be 4 exclamation divided by 0 exclamation times 4 minus 0 exclamation, right? So those zeros, 0 exclamation. Can we do 0 exclamation? Minus hidden in the way with it. This is going to equal just the 1. When we do 4C1, we've got 4 exclamation divided by 1 exclamation times 4 minus 1 exclamation. So this ends up 1 times 2 times 3 times 4, 2 times 3 is 6. So we've got 24. 1 times 2 times 3 is 6. So 24 divided by 6 is 4. First term is 1, second term is 4. Look at that. In our triangle, we already saw that. 1 and the second term is 4. The third one should come out to be a 6. Let's see if it shows us that. If it's 2, we got 4 exclamation over 2 exclamation, 4 minus 2 exclamation. So 4 is 1 times 2 times 3 times 4. We already calculated as 24. 2 times 4 minus 2. So 2 is just 1 times 2. So that's a 2. This is 4 minus 2. That's also a 2. So 2 times 2 is 4. That tells us our third term. So we work through all of those for 1, 2, 3, and 4. 0, 1, 2, 3, and 4. And it'll get us the 1, 4, 6. And we'll end up with the 4 again and the 1. It allows us to jump straight to this line of Pascal's triangle using the binomial theorem to calculate exactly what the coefficients are. What's the first coefficient, second coefficient, third coefficient, fourth coefficient, fifth coefficient? It's 1, 4, 6, 4, 1. Pretty cool thing with the binomial theorem. The binomial theorem. So Pascal's triangle, very useful. Binomial theorem helps us jump if we're not one of the first few rows that's easy to calculate or easy to memorize. If we got to the 15th power, jump down and use the binomial theorem to figure out all of the coefficients, which there would be 16, right? Because whatever this power is, there's one term more. It's first power, so there's 2 terms. Second power, there's 3 terms. Third power, there's 4 terms. Fourth power, there's 5 terms. So 15th power, we'd have 16 terms, but we could figure out what they all are here. Or you can just keep building your triangle down till you get to the 16th. Pretty cool stuff. Cool shortcuts. All right, let's see what else we're talking about in this. Not that isn't enough right there, because that's some good stuff right there. The leading coefficient test, we've already talked some about that. If our leading coefficient is an x to the 4th, we know that the ends are both going to go the same direction, because this is an even number. Anytime you have an even number for your leading coefficient, your largest exponent, it's going to go the same direction. If we have x to the 5th, which is an odd number, that means one end is going to go down and the other end of the graph is going to go up. It could do all kinds of crazy stuff in the middle, doesn't matter, but we know the end behavior, Now, if this is a negative x to the fourth of that, right, so this is when the leading coefficient is positive. We're going to see this. The leading coefficient is a positive on an odd one. We're going to see negative infinity on the left, positive infinity on the right. The leading coefficient is negative. We're going to see downward. And again, it could be, could be a lot going on in the middle, depending on how high your exponent is. But the leading coefficient is negative. If the leading of a odd, it means we're going to be coming from infinity and go to negative infinity on the right. So the coefficients tell us a lot, whether they're positive or negative, and whether it's an even or an odd exponent on the leading, the largest exponent, leading coefficient, tells us something about the graph right away. What else can we learn about the graph? Zeros tell us a lot about the graph. So this is the last part of lesson 2. Some really cool stuff. Let's say we've got a polynomial, and after we factor it, let's say we factor this polynomial, and we find out that the factors are x minus 1. We got 2 of those, and we also have x plus 2, x plus 2, x plus 2. What I found out is, this was an x to the 5th. The original equation was x to the 5th. And when I factored it, I got all the way down to where I just had x down to its basic factors, x plus 1s and x minus 1s and x plus 2s. So here's what I know when I graph that. I'm going to pull up a graph paper here. Here's what I know when I graph that. We know this is the same as x minus 1 squared. Don't want it to look like a plus. X minus 1 squared and x plus 2 to the 3rd power. And leading coefficient would be a positive because we don't have a negative coefficient anywhere. All we have is x's. They're all positive 1s. So we know that this end of the graph is going to go down. This end of the graph is going to go up because it's odd. This was an x to the 5th. And it's a positive. So we could sketch a graph of this knowing just this information. If x minus 1 is one of the factors, that means 1 is one of the zeros, because if we set that equal to 0, x minus 1 equals 0, x equals 1. And we know that negative 2 is one of the zeros. We know these are the zeros of the graph. So at negative 2 is one of the zeros, and at 1 is one of the zeros. What else do we know? We know since negative 2 is, there's 3 of those zeros to the 3rd power. The zeros are actually 1, 1, negative 2, negative 2, negative 2, right? But we only need to graph negative 2 once. But there's 3 of them. Since this is an odd number, that means it crosses the graph there. It crosses the x-axis. But since this one, and I'm going to put this in blue, this is even. It's not going to cross. It's going to bounce. It's going to bounce. So if we complete this graph, and let's do it in green. We know that this is going to keep going down. This is going to come back and connect into here, and then this is going to go up. The graph is going to look similar to that. This is just going to bounce off the x-axis because there's 2 zeros at 1. There's 2 of these. Since there's an even number, this bounces. Since there's an odd number of these, it's going to cross the x-axis. So that allows us to quickly create a sketch of a x to the 5th equation by knowing its factors when we get it down to where we factor it to like that. Pretty cool stuff. If we have, let's see, they give an example in the book is 2x to the 5th minus 6x to the 4th plus 4x to the 3rd. And on that one, when they factor it, the factors end up to be, or the zeros end up to be 0, 1, and 2. because it ends up to be 2x to the third, x minus 2, x minus 1. All right, so we just have 3 intercepts, and there's 3 zeros, really, 3 zeros on there. So that one would graph at the 0, the 1, and the 2. It's a positive, so it's going to come and it's going to cross every time. Every time is a crossing because they're all odd number of zeros. So we can make that quick and easy just by knowing the factors and filling out the zeros on that. So that's pretty cool. Really neat thing. And they talk about the intermediate value theorem. And the intermediate value theorem just says, let me kind of break this down into a nutshell. That says if you have, and it gives you the math theorem, let A and B be real numbers so that A is less than B. And if f is a polynomial function so that the function of A is not equal to the function of B, then in the interval AB, it takes on every value. So it just basically says if we have f of A, if we have 2 points, and let's say right here and right here, and this function is less than that function, that it means that every value between there has a value, right? So it'll say if the graph looks like that. It's just saying the intermediate value is like if these are not equal to each other, which they're not the same point, they're not the same point, they're not, this is a different point. That means in this function, every point's going to exist in between there. And sure, we understand that. Another thing it also talks about is the extreme value theorem, which means if this is continuous on a closed interval, which means there's no arrows at the end, no arrows. If this is continuous, then this has a maximum and minimum. That's what the extreme value theorem says. There is an extreme value maximum and extreme value minimum right here. Right? So the extreme values at the endpoints could be the ends. Like this is the minimum right here, right? That is there. This actually has a maximum right here. But there are extrema. You just have to calculate and see if it says if you calculate the value of x, if you calculate the x right there, the value of what the y is right there, what the function equals, and then the value on both sides of it is smaller, then that's a maximum. If it's higher, then that's a minimum. So that is the we take some test values and you test both sides and determine what's the max and what's the minimum. If we graph it, it's really easy to see that. But basically, the extreme value theorem just guarantees that on a closed interval where it doesn't go to infinity, any continuous function has a maximum and minimum. Sure, that makes sense, but they actually have a theorem that guarantees that. We know for sure it would have a maximum and minimum. That makes sense. If it's a closed interval, there has to be a largest point and a smallest point for a function. So, okay, that's kind of a big top-down look at everything. I think this is one of the coolest things to get out of it is learning that we can graph things based on the zeros and knowing how many of them there are, knowing whether it bounces, whether it crosses, whether it bounces or crosses. So if I just gave you a graph and said, what is the equation for this? Let's look at that real quick. So if I gave you this graph and I said, okay, here is a graph and it's going to do this. You know a lot of things about it already. You know that there's 1, 2, 3. There's a 0 there. There could be 1, 0, 3 zeros, 5. There's an odd number of zeros right there. But we know at least one. So this could be the graph of f of x equals, since this is at -3, it would be x plus 3 would be one of the factors. And then this is 1, 2, 3. That's +3, but it bounces off of it. So at x minus 3 squared. That may very well be the graph of x plus 3, x minus 3 squared. And you could multiply those together to get the actual standard form of that polynomial. But that will be acceptable for this. Now, it could be that this is a third power and that's a fourth power. That would take some more research to know on how smooth the curve is, what is the low point, where does it cross the y-axis. You know, a lot of times where it crosses the y-axis may help determine that too, because we know what the y-intercept, we could calculate the y-intercept by figuring out what the constant is at the end. What's the constant? When everything's 0, if we multiply this together, what's the constant down here at the end? What is the plus or minus value? And that would tell us the y-intercept. That helps us get the graph even more accurate by calculating that last number down there. But we know that this is odd and this is even just from the graph. So a lot of shortcuts. And when you take like ACT and stuff, and so you may have questions like that, where it gives you a graph and asks you what the function can be. And knowing that it has to be an odd number of zeros there, 1 or 3 or 5, and that if it bounces, there's multiple zeros at 3, can help you on the ACT and those type of tests in understanding and getting that right. I know I had to take a math test to be a math teacher, and there was a question exactly like that. It wanted to know what was the function, and it just gave me a graph, and it crossed multiple times. It bounced once or twice, it crossed once or twice, and you just keep adding extra factors on there of x minus 1, x plus 2, whatever it is, squared or cubed or whatever it needs to be.
Let's get out of here. Word to your multiples. Math, baby.